All right, so is my screen visible now?
Yes, sir.
Okay, good. Yes, so where was I? Inherit. This it's here. Right, so we are in the English distance class, and one more class we'll include here. That is, suppose we are dealing with some contractual business where you supply furniture, etc. So you need lumber, and lumber means pieces of wood cut into typical dimensions for constructing furniture or even doors and windows. Anyway, so the dimensions of lumbers are also required, and we already have this. I had started writing this class type last time. Class distance is also there. Okay. So we'll just see how inheritance works for a special type of function, that is constructors. So quantity and price of number and public. So we are writing the let's just recap. Where is the where are the constructors of these things, and so this is our no argument constructor, right? And this is our two argument constructor for type, and for distance again. This is the no argument constructor, and this is the how many are there? Two argument constructors. And for number, we will have so this is again no argument constructor. And dimension. Sure. But in quantity and price. dimensions and grades. Okay. And this this constructor has 1, 2, 3, 4, 6 arguments. Okay. And we need a print function for show number type. So the scope resolution operator says that we are accessing its show type, right? Just no show type here. Should write a show type. Get type is get type. What is it? Oh, it's not taking all the values. Yeah. So let me complete writing this one. Normal dimensions. Say 2 plus 4, etc. In dimensions, Sept, enter grade, which is rough. In grade. This is a print function, so it's constant here, and Sept. Then dimensions, so this is a show type for the class type, and now we can invoke show type from class type using the scope resolution operator. We have show list here, right? It's there. Instance. Price we want to display in dollars. So the total price is like price per unit into quantity. Okay. So this is not required anymore. And let me comment. Oh, I should have saved this before. Okay, let this be. right. So number signing constructor is called Sept. So because we have declared an object of lumber. Oh, sorry. This is also not this sign, right? Not required. Actually, we can. Yes. Lumber is inherited from, lumber is derived from type and distance, whereas type and distance are like two kind of disjoint, two separate base classes, not having not being derived from one another. But lumber is derived from both. Okay, public derivation. So, all right, and yes, I hope the return function. Okay, so we have declared an object of the lumber class, and automatically the no argument constructor is executed. Okay, now siding, better put an index here, siding data, and then siding gives number. It asks you for the data, asks the user for the data, and so this was invoking the no argument constructor, or we can do this. Starts. Here it will say like, so what was the thing? Okay, dimensions versus dimensions. So let's do 2 cross 4. Constructor grade is sorry, what am I saying? There's a lot of const here. Something is constructor, some is constant. So here this means construction grade. Okay. And next is how many feet, or what is grammatically correct? Maybe foot, whatever. 0 inches, and quantity is 200, and price still 4.45. So this invokes the 6 arguments in there, right? Yeah, 6 argument function. And then siding and then starts. let's see how this, whether this works or not. And we are here. Okay, lots of typos. This is 96. Sorry. Get number should be included, and for type it will call get type. Distance it will call get distance. Number of distance. Get test. Quantity price, okay. So we see this also 120, that is 2. Okay, so it is not declared here. All right. Enter nominal dimensions. And this is so what should we write? That this is a string. So 2 cross 4 is given in the later one. So maybe 1 cross 2. Rough. That is 8, right? This will be 4, 0. Quantity give me 100. Price per piece is said to words. Right. So this is how, I mean, yeah, it's not very different from usual functions. So one more thing. Okay, so this is from the function example that we did before. This is kind of straightforward. It's not fundamentally different from that. So in this example and the other example, what we have seen is that each, like some more slightly more sophisticated examples we did last time, and we saw that I mean, at the end, the class that was at the lowest level, it had like a unique path from each derived class, like from each parent class, or from each base class. Okay, so maybe we derive like from A we derive B, then we derive C, and maybe from D we derive E, and from E also we derive C, something like that. So if you consider the, like, yeah, it was a directed acyclic graph. It didn't have any cycles otherwise also, if you ignore the directions in the, like, derivation tree. But what if it does have cycles in such derivation? Then what happens? We will see that. This was inherit 10, so 11. What I'm saying is that, see here, I mean, C is the root. No, sorry, C is not the root. So it's a kind of multiple root thing. So at the highest level you have A and B, and then you have C second level, and D from there. What if we change this a bit? So again, I want to demonstrate some ambiguity in multiple inheritance. What I want to do is say, okay, this is C, and so let's try. So at the first level we have A. Actually, let me let's put A here and B and C, and I will just reverse the arrows. Okay, so that means that both B and C are derived from A. Okay, and I want to create some ambiguity here by doing the following. So that means that basically from A we are deriving B and C, and from B and C we are deriving D. So like kind of a loop or diamond shape. Okay. Yeah. So we have B and let's put something. Okay. We have one function can be accessed by anyone from class A and B. Yeah, I don't need this. So there is only one function, that is public data A, and let me also make one duplicate. This is public inheritance A. This will be C. Public A, and finally we will have class D, which is public B and C. Okay. Oh, we had one. Oh, sorry. We anyway, forget this. We don't need it. Just let me see if this compiles or not. Okay, fine. Yeah. So what I was saying is that B and C are derived from A, and this is D is derived from B and C. So there's only one function. Okay, that is there in A. And if I now say this, let me create an object of D and D object D. Dot, what is our function? Put data A. So I'll come to this. Just to check, if I use the scope resolution operator, then it is all right. 1 second. So no, it is not. It is not all right. Let me just go further down. If I have this. If I say this object is put data B, okay, so I'm making some mistake here. This is public, right? And oh, sorry. This is like data B, right? Okay, this is C. I didn't make a copy in B. Put data, and this should also be put data. All right. Silly mistakes. If I do this, there'll be an ambiguity. Yeah, there'll be an ambiguity. But if I say this scope resolution, if I use, then there'll be data, no matching function equal to. Oh, so this sorry, this is I made a mistake here. It should be C because the function is in C. Okay, this is fine. This is fine. Now, okay, but this we had seen this before because C is in the C is referred to explicitly through the scope resolution operator. So it is like this. Our earlier problem in this the error in this was coming because I had written some put data A here and I was calling put data. So mistake on my part. Yes. So now there's only one put data function, and yes. Now if I use scope resolution operator, it should no. So first, let me do this. Okay. This is ambiguous, and what if I write so scope resolution operator? If I so you can see that there is no escape in this one. Earlier, when we had different bases, and so maybe from different, so A is the base for B, B is the base for C, C is the base for D. If we had a linear relation, then we would easily solve, this problem by using the scope resolution operator. But here you see, we don't have any choice. Like, if you put just put data, if you just invoke put data, then it's saying it is ambiguous. But if you use also the scope resolution operator, then also it's ambiguous. Why is this? Because how does inheritance work? So when you derive a class from another class, the members of this class, the base class, have an implicit copy in the derived class. So as soon as I derive B and C from A, it is so the members of A are being implicitly being copied into B and C. So put data is copied into B and C. And now when I say that I call the scope resolution operator. I invoke put data of A through scope resolution operator. It is looking for the inherited copy of the put data of A inside B and C. And since B and C both have copies of this function, they don't make any change or anything. But so for this, it would not matter if A was put data was called through either path, but the compiler does not understand that. Since A is A is an ancestor of D through two paths, through more than one path actually. It could have been 3 or 4 paths also. It gives it shows an error due to ambiguity. Okay, because A is an ambiguous base. Because between A and D you have multiple paths. So steer clear out of such problems. Okay, so this was inheritance when the underlying undirected graph has a cycle, and not much is left afterwards. So aggregation means usage. Okay, so this is not much to look at. We're almost done with inheritance. So it's yeah. Let me just keep this and so yeah. If we did something like this, say plus E. Let me eliminate this guy first. Oh, this is 12. Fine. If we do something like this and plus F, which is E object E. So this is something fine which is allowed. You might as well use this, and so it's a special kind of association wherein one class contains an object of the other, and that's how you can make things more sophisticated. And some maybe a little bit of okay, one more thing is there, and there's something called composition, which is basically a stronger form of aggregation, and so this so where we can so where one class may be composed of multiple objects of other classes, that is all right. And so let's we have 15 minutes. Let's see a concrete example of aggregation of classes, and we will be done with inheritance. So our employee program, and we'll write this again. Yeah, what will we have? That's student plus employee plus manager, and we have this. Class labor or class scientist maybe. So this guy is also an employee. And we can just so is this allowed? Right. we'll expand this with school. So for the students, it's just school and degree. And class employee will have employee name and employee number, and public void get data. And we have void data. Right, so these didn't have, I mean, objects of other classes. Now we'll have. The title, vice president, etc. call subdues. Yeah, this we had, and we have these two objects. Now, public. So void get data. And we had a get data, and we will have stu dot get. Wait, what did I do here? This is our get data, and void good data will be const, and we will put employee good data. Yeah, let's get rid of these two. Okay, and we can have our main function here. Just let me compile it. It's fine. Manager M1, and so Sept. Enter data for manager 1. M1 dot get data, and yeah, that's it. And we can say Sept. Data for manager 1. We'll just say M1 dot put data. So here last name Jones, employee number, title VP, Where is it from? So maybe Celtic, ISTQS, MS. Yeah, so this works, and you can now use an object. So basically, use and create aggregation of classes in this way, as well as composition. Yeah, so pretty much this is what there is in inheritance, but we left a lot of things in overloading. Polymorphism, actually, yeah, even after this, doing the remaining things in overloading, we'll still learn other stuff in polymorphism. So we'll finish off operator overloading, and even some things if we have left in function overloading tomorrow. And I'll see you today in the lab.
Sir, what will be the topics of today's lab, sir?
Today there will be algebra.